everyone. I just want to remind you that you have 2 bonus assignments due on Friday at 11:59 p.m. The survey will just take you a few minutes if you haven't already done that. And this bonus R problem, you have to allow yourself more time for. Also, the homework 5 is posted, and at the end of this lecture, you'll be able to have all the information to do that. So let's go to the document camera now, and remember where we left off. It was on page 32. We didn't complete the summary for simple regression. Okay, so you need to know for the exam, and so commit this to memory, that the slope of the regression line is the correlation coefficient, R, times the ratio of the standard deviation of y to x. And those of you who are worried about whether the standard deviation is the sample or the population, you don't have to worry here because it's the ratio of them. So if you divide by n minus 1 or n in the denominator, it will cancel out. It's just pure units, so it doesn't make any difference. Just those of you who worry about that, okay? So it's just the standard deviation of the y over the standard deviation of the x. Okay, now the typical error around the regression line is, we're calling it the standard deviation of the errors, and it's the square root of 1 minus r squared times the standard deviation of y. And we can adjust the standard deviation for small samples. We'll do that later, but just now, let's just keep it like this now. Okay, so it's also called the root mean square error because that's what a standard deviation is, the square root of the mean of the errors. Okay, now this, don't worry about memorizing this right here, even though a lot of you already know it from Stat 100 because you had to memorize it there, but this will be given to you on exam 1 and probably on the other exams too. But for now, exam 1's coming up on the 12th, so that will be given to you February 12th. All right? Now, the other thing that's really, we talked about this little r squared, you're going to encounter this a lot as a capital R squared, especially when you get to multiple regression. And it's the proportion of the variation of the y's predicted by the regression line. And then 1 minus r squared is the proportion of the variation of y's that's left in the errors, the scatter around the regression line. And so this r squared, since we're going to be seeing it over and over and over again in this class and in others as well, because it's featured, r squared is featured in all regression analysis. Here, let's zoom out a little bit. Okay, so this r squared, right, can be thought of as like it's the correlation in simple regression. It's the correlation coefficient squared. So it's like the signal, and 1 minus r squared is like the noise, right? So this is the signal, the pattern we're looking for, and this is noise, just random error, and it has to equal 1, of course. Right? It equals 1. So when you multiply both sides by the variance of y, so you could get r squared times the variance of the y's plus 1 minus r squared times the variance of the y's is equal to the variance of the y's, right? Well, this right here is basically how, when you do something called analysis of variance, you partition the variance of the y's, the spread around the y's, what you're trying to predict, what you're trying to predict, into 2 parts. One is indicates the strength of the model. In this case, our model is the regression line. So this is the strength of the model, the signal. And this is the strength of our errors. Okay, so partitioning, this partition right here, this partition is called analysis of variance, abbreviated ANOVA, and it's going to be the way that we're analyzing the strength of our linear models throughout the course. So I just wanted to give it to you right away. I mean, that was my purpose in giving it to people in Stat 100 like this, because it follows so naturally into analysis of variance, which is something we're going to be doing a lot of in this class and in all regression classes that focus on regression. All right, so that's to come in chapter 11. But before we do that, we're going to look at, it's used in inference for linear regression, right? Inference. So now we're going to talk about using regression to make statistical inferences. So far, we've just looked at regression descriptively. Back in Stat 100, that's all we did, and in most AP Stats classes, that's all you do. I mean, in most first semester Stats classes. You just analyze the relationship between two sets of numbers by drawing the scatter plot and by calculating the correlation coefficient R and the slope of the regression line and the y-intercept, right? But now we're going to do something, now we're going to use regression to make inferences about a wider population, okay, from our sample. Just like we did when we made inferences about the mean, about a population mean from a sample mean. Back in Stat 100, we used sample averages and percents to estimate population averages and percents. And then we put error bars around those and confidence. We built confidence intervals by computing standard errors and then using the normal curve or the t-curves to compute confidence intervals. For the mean, we use the t-curve. For the percent, we always use the z, the normal curve. All right, now we're going to do the analogous process with our regression statistics. Okay, so basically we got this regression equation, we got a slope, that's our sample slope, right? But each time we take a sample, that slope will vary. So we want to describe the typical variation of that slope and put confidence intervals around the slope. That's what we're going to be doing. All right? But to do this, we need 4 assumptions. And these 4 assumptions you'll see in all regression analysis, okay? It's linearity, that the plot, the scatter plot follows a linear pattern, not a curve, like not a parabola or some kind of exponential curve or anything, but a linear pattern, that the errors are independent of each other, and that they have equal variability across the whole, all x's, and that the errors are normally distributed. Sometimes referred to as that the errors are independent, identically distributed, normal 0 sigma squared, IID normal 0 sigma squared. If people are in higher level math classes, you've probably seen that a lot, stats classes. All right, so things are going to get more complicated, so let's just start using some formal notation here so we can distinguish what the slope, our sample slope from our estimated ideal population slope, etc. Now remember, we use these Greek letters for the population parameters, and in our model, this ideal model now that we're building, and we use the Roman letters for the sample statistics. Okay? And we use those sample stats to estimate population parameters. So, and then we put something called a hat, like on our predicted values. So here we go. So for our population model regression equation, instead of what we've been doing before. We said basically y equals mx plus b and put the intercept second. Usually the way you write it is like this with a Greek letter beta, and beta sub 0, beta naught, that's the y-intercept. That's one of the parameters of the population you're estimating. So that's the y-intercept. Like if you're doing y equals mx plus b, that would be the b, right? And then this, it would be the m. If you only have one x, like we do now, I'll just put 1 for 1x. You'll have a slope associated with that. And this is the population slope right there, beta 1. We're labeling them with numbers because we're going to add other predictor variables. For example, here we're predicting, in our example, we are predicting final scores for a group of Stat 100 students from their exams. Well, what if we also wanted to add homework? That could be x2 added on. And then we have some error, right? Because we know there's scatter. And so the error is, this says the error, these are the error assumptions, that it's normally distributed with the same variance everywhere. And I should have said an independent. The errors are independent of each other. So these right here are our error assumptions. The independence, equal variability, and normality, those three. The linearity is just looking at the plot and does it look linear or not? But these are the error assumptions. Okay. So that's our population with the Greek letters. And now our sample regression equation has the Roman letters. And this hat over the y, notice I have no error term here because I'm saying our predicted y with the little hat over it is equal to our sample statistic that we got for the y-intercept plus the slope times x, okay? Where y, see, y is an observed value of all the y's, and y hat is a predicted value of y. If I just put the little y without the hat on it, I would have had to say plus e, plus a Roman letter for error, okay? For all, but when I make this is just the prediction. Remember, the prediction is that point on the line. Of course, there's error around it, but I don't have to include it here if I put the hat on. All right, just language there. All right, so now let's go back to this example that we used. And the example was the finals and the exam scores of a group of Stat 100 students. And now, suppose those exam averages and final scores of the 100 Stat 100 students from the previous example that we just looked at in the last chapter were a random sample from a much larger class of all Stat 100 students. Let's say that 2,000 students, okay? How could we use the sample slope in our regression equation to predict the finals from the exams to estimate the population slope? Okay, so let's say this was our sample statistics. So we got 5 sample statistics, and from them, we're going to do exactly the same thing that we did before, but now we're going to imagine that we're going to estimate a wider population of students, okay? So our probability model would be what? Set up a probability model. Imagine we chose 100 points at random without replacement because they're separate students, each one's a separate student, from a scatter plot depicting all 2,000, right? So you would you'd have this scatter plot. So we would randomly select n equals 100 from all 2,000 students in the population. So this is our sample and this is our population. From all 2,000 students in the population. So the idea is that there's some scatter plot here. I'm just going to draw the first quadrant because everybody has positive exam scores, right? And so these are the exam scores of all 2,000 students. And these are their finals. That says final scores, exams and finals. And then imagine that there's 2,000 points in here, but we don't know what we don't have that data, right? It's just suppose we just randomly, so there's this population out there. We don't know what it looks like, right? And that we randomly draw out of here, out of the 2,000, we randomly draw 100 little points, okay? And then from that, we get a sample scatter plot, okay? And that sample scatter plot we'll say is what we looked at last time, because we had 100. We'll say that's what we got. That was our sample, all right? And the first thing we want to do is to make sure, if we're going to be doing inference, we didn't have to do this if we were just going to do descriptive statistics. We didn't have to. These allow us to do, you'll see why, allow us to do inference. So the first thing that you have to look at is, does that plot that we got look like it might well be fit with a straight line plus some scatter? Could we fit it? If not, if it looks like there's a lot of curvature, then we're going to have to do some other fit, like we'll have to fit a curve or make some transformation of the of that variable to make it look more linear in order to allow us to use these linear models. And that will be coming up. We'll be doing that later in the semester. Okay? We'll look at what happens when we have a curve instead and how to handle that. But right now, let's say if the plot looks linear, then we can go ahead and fit the regression, the linear equation, to that plot. So the first thing we want to do is we want to check linearity. In the sample scatter plot. Remember, we don't really know that one. And many times that's just imaginary. We're just imagining that. Okay? All right. So we want it to look like, basically, ours did look pretty good. What's good? If a good plot would look like, it would show a linear pattern, right? Like sort of just, as X got bigger, so did Y, or vice versa, or even just a random pattern would be okay. That's good. What would be bad is any kind of curvature. So, for example, something like this, like where it's not linear. See, something like it's a clear curvature. We wouldn't want to fit a line to that because we could do better with a curve. Okay, that would be bad. There's lots of examples of bad, any type of curve. You might just see some other type of curve like, I don't know, just has something like that. That would be bad too. Just because it's clearly has some pattern and we want to get the best model and it's not linear. Okay, so those two, okay? So now, let's say it looks like this. It's good, and it was. And then, from the previous page, what did we do? Well, from this, we got the regression equation. So now, let's put it, here it was. I'll show it to you, like what we did last time. Right here, we said the final y equals, we did like mx plus b form. That's what people are used to. So we said y equals the slope times x plus the y-intercept. All right, so now we're just going to write it in the statistical form. The same thing that we got. So it's the same thing. And now it's our predicted y. This is our sample regression equation. Is equal to, now you put the intercept first, beta naught, that's the first thing, 18, plus 0.67x. All right, that's final. Our predicted final equals 18 plus 0.67 times the exam average. And this is from the previous page. From page 31. Okay, so that's nothing new. Now what we want to do is we want to get a standard error for that slope. Okay? That's what we're going to think about now. So our sample slope, right, that's the Roman letter B for the just one slope here, is the best estimate of the population slope beta, right? It's the best. What else would we use, right? It's the best. But of course it won't be exact, since each time we take a random sample of, let's say 100, another 100, we'll get a different set of points. So our sample slope will vary by give or take what amount. So how much the slope typically varies is called, of course, the standard error of the slope. And it follows its own square root law, meaning that the square root, it's an SD over the square root of n. Just like the average, the standard error of the average and the percent is the SD over the square root of n. Okay? Now, I'm just doing it for large n first, and then we're going to adjust it for smaller n later. And 100 points is a large n. It's pretty large, so we're just going to, okay? So this is just, we're not going to make any adjustments to n here. All right, so now let's look at this slope. This is what it is, standard deviation of the errors. So it looks like SD over square root of n. This is probably confusing to you. Why are we adding that? That probably would make complete sense, SD over square root of n, right? The formula makes sense. Why? Because the variability of the slope comes from the random errors of y around the prediction line. Remember what the standard deviation of the errors is. That's those standard deviation of the errors is the scatter. It's a measure of the scatter around the regression line. If that was 0, if every point was on the line, there'd be no sampling error. There'd be every time, no matter even if we picked 3 points, we'd get the exact right line. So the more error there is, the more standard error there's going to be, right? The more scatter. So doesn't that make complete sense? Does it? Not if it does. That would be in the numerator, right? This is your sampling error. This is how much, every time you take a sample, how much your slope is going to vary, right? If it had no error, if it looked like this, then every time we took a sample, let's say we took any 3 of these points, we'd always get the same thing if it had no error. If it has a lot of error, then we're going to, look, we could get these 3 points. We could get our slope's going to vary a huge amount. And it's going to vary, the more scatter there is, it's going to vary. And also, the bigger our sample size is, the less it will vary. I was only taking 3 points, so it could vary a whole lot. If I took a lot of points, it's going to get closer and closer to the true population parameter by a factor of the square root of n, just like with the average, like everything else, that error scales as the square root of n. We've seen that before. So that looks perfectly fine, right? But what about this SDX? Well, here, I think you'll understand it. Let's rewrite this. The standard deviation of the errors we saw last time is the square root of 1 minus r squared times the standard deviation of y. So this is what we have so far, okay? So this is described, these standard deviation of the errors is described in terms of y, and slope is change in y per unit of x. So we need to divide by SDX. This is a standard error of the slope. It's going to be, you're going to say the slope is such and such plus or minus such and such. It has to be in the same units of SDY over SDX, because that's what the slope is in. So that's to make the units right. So that's where that makes sense of that formula. Okay? Any questions on that? Any questions on that? All right, so that's the formula. And again, because you have a lot to remember, I will give it to you in either this form or that form on the first exam. So one of these will be given on exam once, because you're just so you don't have too much to remember. Okay, now let's see. So I said that you need assumptions 2 and 3 to do this. Why? All right. So why do we need assumptions 2 and 3 to derive the standard error of the slope? Well, okay. We need independence because this square root of n here, what is that? Okay, so that's the sample size. If our errors are dependent on each other, for example, if let's say there were a lot of identical twins or triplets in our population, then we'd really, so if we got one twin, you know, they're going to be very much alike, so the errors would be dependent, then we wouldn't really have as big an n as we thought. If they're correlated errors, then this n, we'd have to adjust the sample size. So the errors in the true underlying regression model must be mutually independent. The idea is, can we model our data as random errors, random draws, excuse me, from a larger population? All right, can we do that? Model as random draws so that when you pick one point, it doesn't determine what the next point would be, or it doesn't change the odds of getting the next point. It matters. So how can we check this? Your plot, your scatter plot, and we'll look at this in a minute. Your scatter plot and your residual plots should show no grouping. Okay? For example, if there's many identical twins, then we don't in effect have as big a sample as we thought. So we want to check, before we talk about the residual plot, let's just stick with the scatter plot because I haven't introduced the residual plot yet. So check that just your regular scatter plot shows no clumping or grouping. That's a good check for independence. So for example, so again, I'm just going to do, this is good. This is, so far that would be good. Just looks like our last one. But what would be bad would be something where we had sort of the same thing, but then you might have like a whole group of people there, like all together, or something like right there, right? Or maybe another one down there, something like that. You really don't have as many points. If you counted all those individual points, it wouldn't be right because you really don't have as large an n as you'd think. So that would be bad, the grouping. Okay? Then our assumption, our third assumption, which is, these are really important assumptions, both 2 and 3, is that equal variance. What that means is that the spread around the regression line should be the same across all values of x. So let's just do that. Again, it would look, here I'm just drawing the same type of plot, like this, right? That might not look like the spread's the same, like it looks like it's biggest in the middle here, but that's just because there aren't that many points here. If there were the same, often you get this elliptical shaped cloud, but if there were the same number of points here, then there would be the same spread. It's just because, there's just not that many points up here compared to here. All right, and what would bad look like? Bad would look like the most typical way that you see bad, and you'll see this a lot in our Stat 100 data, is something where you have a fan-shaped plot. So it's something like that. Well, you still fit a line, it's linear, and there's no grouping, but as x increases, so does your error increase. We see a lot of that. And why is that bad? Why is that bad for, why can't we use this particular standard error formula? That's what I'm saying. We'd have to transform it to use it because how much, what we're trying to look at is how much the slope is changing, right? And if we get a scatter plot like this, that indicates probably in our population it looked like that, which means that it's going to vary more, because changing y near the middle, like changing y in the middle, isn't going to change your slope very much, but like at the edges, it does. It's going to really affect the slope. Changing y at the extreme pulls the slope down or up. And same if it was at that extreme. So there's going to be more variability. We'd have to increase our standard error if we have a distribution, underlying distribution that looks like that. Okay. And we'll look at ways to correct that. I know this is probably, this is pretty technical, but it's sort of the basics of what you have to know before you can start inference. Yes? On an exam, I might ask you, like, give you different pictures and say which one it violates. Like this would violate equal variance. Something like that. Other bad examples would be just anything, okay, what you want. It's easier when you look at the residual plot here, but basically you want, here's another bad example. You could have a fan shape like that. You just want across the regression line, you want it to look like this. Whatever plot you have, you want it to be equal all the way across, okay? Now lots of times it's not equal. It looks like this. So it's kind of deceptive, but that's just because there's fewer points here. Does that help? All right. It's much easier to tell from these residual plots. I just want to sort of, okay, so now to check the assumptions, you can look at either the scatter plot or there's something called the residual plot. But it's usually easier to spot these assumption violations by looking at the residual plot. And you'll have an example in your homework where you'll see how much easier it is, just because the scale of the residual plot is different. So look at the scatter plot and residual plots below. Do assumptions 1 through 3 appear satisfied? And so this is our actual data here. And how do you get the residual plot? Well, the residual plot is plotting these, instead of plotting y here, you're plotting your errors around y. So for example, you're plotting that distance right here. You're straightening out this line because the errors, the average of all the errors is 0, and you're just straightening that out and you're saying, how far off the line is this? And this looks like it's about what? 15 off the line, so you can read it more easily. Here's another example. Which one would this be? That's this point right here. And it's easier to see. For example, you can see it's 20, that's an error of 20. It's negative, so that would be this point. So it's just easier to check these assumptions looking at the residual plot. You're checking the same thing. Now, so let's go through it. So we look, first of all, it looks linear. There's no real clumping. Now, there's a lot more points around the line just because that's how you draw the line. It's going to be more, you know, they're not going to be as many points far off, right? But there's no grouping, and it really doesn't have a fan shape. I mean, it's pretty obvious when it does. Okay? Does that help answer your question? Okay, so now we'll attach the standard error to your estimate for the slope to give it a range instead of an exact point estimate. So this is what we've done before. So to give it a range, what are we going to do? We're going to say, okay, so the standard error for the slope, I'll just write it like this for now. You could put a B down there. Standard error for the slope, let's remember what it is. It's the standard deviation of the errors over the square root of n. That's how I remember it. But then I say, oh, right, then I have to adjust for this s dx to make it match because it's a slope. All right, so we remember that's the square root of 1 minus r squared times the standard deviation of y over the square root of n times the standard deviation of x. So now we have to look on our previous page for these statistics. I remember what they were. Remember r was 0.6 squared, and n, our sample size, is 100. And then the ratio of the two standard errors. Well, I'm going to have to go back and check. And it was, okay, there they are. So y over x is 10.3 over 9.2. And that's approximately equal to 0.09. So that is our standard error of the slope. So we're just going to attach that. For now, remember our slope was 0.67, right? That's what we calculated before. Our slope was, here it is, 0. So we're just going to attach, instead of just doing that point estimate, some wiggle room. And then we're going to look at how to build confidence intervals. But for now, let's just attach the standard error to it. So 0.7, give or take what? Give or take that. Okay? So we'll say our slope, so give it a range. So our range would be, so the range would be equal to our sample slope, which is 0.67, plus or minus 0.09. So that would be 0.58 to 0.76. That's our range. Okay? Now we're going to have to use some more, now we're going to have to look at how to build confidence intervals. What I mean by that, how sure we are that the slope is in that range. Okay, so far, so any questions? All right, let's go then. All right, now confidence intervals. So, how confident are we that our population slope is, in that range? How confident are we that the true population slope will lie in that range we just calculated? All right? So how sure, it's the same thing as saying, how sure are we that if we actually calculated the true slope for all 2,000 points, we'd get a slope within that range? That's what we're trying to answer. Okay? And in the past, you've seen that we can use the normal curve to answer that question when we have a large enough sample size, when n is big enough. Because, and you've seen this in the bonus review exercise 1 you did, you saw that the probability histograms for the sum of n independent draws from a box of numbers is going to, for the sum of that, the histogram of the sum is going to look normal as long as n is large enough. That's one of the most important, most beautiful theorems in all of statistics. I think it's gorgeous, called the central limit theorem. And and that doesn't depend, you can have a very skewed distribution of numbers. It doesn't, the actual distribution of the numbers can be extremely skewed, but the probability histogram for the sum of those numbers, which means for the average and percent too, because that follows from the sum, would be distributed normally as long as your sample size is big enough. Okay? And since the slope, the errors in our slope come from the sum of n independent errors, then we can apply the central limit theorem to the slope. So as long as n is big enough. So with the big N, we can use the normal curve. So then you what's called the sampling distribution, right? This sampling distribution of the sample slope of our sample slope this is this right here. The normal curve is the sampling distribution of our sample slope when n is large. We're going to have to use t-curves when n is small. All right? And so what the idea is, what? If you have the actual population of we know that if we took thousands of random samples of n equals 100 from the actual population of 2,000. So imagine doing this. You have all 2,000 points and you take samples of 100, and each time you take a sample, you record the slope, right? Then you know that you're most likely, right in the center would be your true population, beta. That would be your true population right in the center, but it's going to vary, right? You theoretically could get a, slope of, whatever. You could just get it as high or low as, anything. But right in the center, could go as far as you want in either direction. You could get a huge negative slope or a huge positive slope. But it's very unlikely. All right? Now, and as a z-score, right in the center would be 0. And this would be 1. That would be 2. That would be 3. That would be -1, -2, and -3. All right, so that's what it looks like. And then 68% of the sample slopes, 68% of them lie in this area. 68% of the time, you would get a sample slope within one standard error in either direction of the true population slope. And 95% of the time, you would get a sample slope, 95% of the time, between 1.96 and -1.96, between about 2 and -2. All right? Now, we don't see all these times. All we see is one particular sample. But since 95% of the time we'd be within 2 standard errors of the true population, we can be 95% confident that our particular sample size slope is within that range and doesn't stick out over here. That would only happen 5% of the time. We don't know for sure, but we think that that's what a confidence interval means. It means we know for sure that when we do this, and you can simulate it and prove it too, that when you do this, that as long as your sample size is big enough, that this is what the distribution will look like. So since 95% of the time, your slope will be within 2 standard errors above or below, then you just figure when you just see one sample, you don't have to see all the others, you can be 95% sure it's in that range. So even if it was right at the edge, if you went over 2, you'd capture it in your range. You wouldn't be centered at it, but your confidence interval, 95% confidence interval, would include it. Right? But if you're over here, and 5% of the time you will be outside that range, like 2.5% time over here and 2.5%, then if you just go over 2, let's say you're up here, if you go over 2, then we don't capture it. The range would go from here to here, and you would not capture it. That's the idea of the confidence interval. Okay. So now, so a way to write that, our confidence interval, is our sample slope plus or minus, like you don't have to do a 95% confidence. You can do any confidence you want, and the width of your, I mean, if you want to do a 68% confidence, it would correspond to going over 1 standard error in either direction. And so the level confidence interval is the width of your confidence interval is given by the critical value of the z-score corresponding to that middle area there. So that's what I say here. So let's do an iClicker question and say, okay, so it's of this form. So let's just say for the 95, what I mean is this. So let's look at the back of the book. And so if you want a 95% confidence interval, you'd look, and we're going to do an iClicker question really soon, we'd look here, and at 95% that's where I'm getting the 2 from. If I wanted to be more exact, it would be a middle area of 95% corresponds to, more accurately, 1.96. And if I wanted to be 68% sure, then it would be correspond to a z-score of about 1. If I wanted to be 75% sure, 75% confident, then it would correspond to a z-score of 1.15. That's called the critical value of z for a particular confidence level. It's just like what we've been doing before for p-values when we did, and for type 1 and type 2 errors. It's the same idea of, you know, just looking on the normal curve and seeing how far out you have to go to get whatever percent. This time we're looking confidence intervals deal with the middle area directly, so this is even easier to do than what we did with our type 1 and type 2 errors corresponding to particular z-scores. Okay, so this table really translates nicely into confidence intervals, which is why I like it so much. All right, now, so this is going to be our iClicker question. Suppose we want to be about 80% confident, and so you can look at that. This is it. This will be our question, and let's just answer it with the clicker. So let's go back over here, and whoops. We'll do these later. Let's just go to this one. All right. And now, all right. So just answer this. I'll get this out of your way so you can read it better. Okay, I'm going to cut it off now and stop it and see how you're doing. Okay. And so the answer is 1.3. And let's see. Great. That's our best yet answer. Yeah, terrific. Okay. So let's just go quickly to the document camera and write that down. Okay. So now, that's called the critical value corresponding to the given confidence interval. All right? So, what we want is okay, so suppose here's our question. So we can say the critical value, you put a little star for the critical value, all right, for the 80% confidence interval is approximately equal to 1.3. Because when you look at the normal curve, 80% of the area of the normal curve is between negative 1.3, the z-score of negative 1.3 and positive 1.3. All right, so let's say we wanted to find 90 and 95% confidence intervals for the true population slope. So we'll use that 90 and 95. So an approximate 95% confidence interval is your sample slope. I'm just doing this, 0.67 plus or minus the z-score, 1.96, but so we can do 2, so we can do it more easily in our head, plus or minus 2 times our standard error. Now, what was our standard error? Our standard error was right here. So plus or minus 1 standard error was 0.09. Okay, so that's going to be equal to positive 0.49 all the way up to 0.85. So we're 95% confident that our true slope is in that range. And if we wanted to do a 90% confidence interval, we're not going to be as sure here. 90% confidence interval, we're not as sure. We're only, so then 90% corresponds to what? The critical value would only be 1.65. So we're not going to be as sure, so it will be a smaller range. If we wanted to be 100% sure, we could have a really big range. Okay, so that's 1.65. That's our critical value times our standard error. And now we're going to get a wider confidence interval. Indicating we're not as sure. Narrower confidence interval, excuse me. Boy, that was confusing. It's narrower. If you wanted to zoom in really, really, really close, then you could zoom in, but you couldn't be as sure for the same sample size. So that's a narrower confidence interval because the z-score is narrower. The z is less. Okay, any questions on that? So now let's look at this question. We'll do another iClicker. So read this question and question part 7 on page 35. And let's make sure you understand to which population a confidence interval can be applied to. So let's look at that. And here's our next one. So that's the 95% confidence interval, but we can be 95% sure that the true population slope of the regression equation for predicting final scores from exam scores, for which population can we apply it to? Can we apply it to the female students in the class, all female students within that 2,000? Can we apply it to, whoa, what happened there? I'm really sorry. That screwed up. There it is. Okay. All Stat 200 students or all 2,000 Stat 100 students that we drew the sample from? Which one? Okay. I'm going to cut it off right now. And let's see what you said. Great. You're doing great on these. Okay. So let's write that down. And go back to the document camera. All right. So the answer is C here. And this is important, that a confidence interval can only be applied to the population the sample was drawn from. Not to a wider population, most people know that, not to a wider population, but also not to a more restricted population either. Not to a wider population and not to a more restricted population either. All right. So let's see what we're going to do now. Let's look at another example. And this is an example. Any questions so far? Yes. That's what most people have a problem. Why can't you apply it to a more restricted population? Think about when we do, a good example would be like when we do political polling, right? Let's say you did a political poll and you found out that like, 48% of the people were for Trump or something before the election, right? A pre-election poll. That doesn't mean that that would apply, that 48% would apply to, for example, college students, even though, or would apply to, for example, blacks. That certainly wasn't. He was very unpopular among certain populations. It just means as a whole. Does that make sense now? It's a good question. It's good. Interesting, yeah. You can't, it depends on if female and male scores are different, then they might, like when we split, we will see some differences. How well their exam scores predict their, homework might be more important predictor than exams or something for one group or the other. Does that make sense? Yeah. Okay. But I'm glad you asked that question because people always, they learn it, but they don't know why. And that, always think of examples. It really helps me understand stuff. All right. So now let's go to the next one. Now, speaking of another good example. So this is looking at data relating GPA to drinking. I'm sure you've all been told that, don't drink too much because, your schoolwork will suffer, among other things. And that might be true. It might not be true. But, and it might be true, so we're just going to look at the data. That's why I love statistics so much, is because we don't have to, we can just look at data and examine it, and the data and just try to understand it instead of taking things at face value. So here's our GPA versus drinks example. And I ask you this question on your survey too. It's due Friday. By the way, please answer honestly so we can collect decent data. And then the truth is so much stranger than fiction. It's stranger and more interesting. And we're the only people, we have, it's extraordinary that we can do this. I mean, nobody else can get their hands on data like we have. And, that's why I'm just using it for us to help us learn better. I'm not going to be, I couldn't ask all these questions if I was actually going to publish anything about this kind of stuff. The interesting questions about social behavior and stuff that people aren't very open about. But it's all anonymous. There's no way I can tell what you write. So please, let's just try to be honest so we can learn stuff. Okay? So suppose I asked a random selected group of U of I students how much they drank per week and what their GPA was. And let's just say I got these 5 sample statistics. All right? So the average number of drinks per week and the average GPA, these are made up, but they're, very loosely based on some past Stat 100 data. So now we're going to set up this probability model, and that means we're going to do the population scatter plot. So it's going to have thousands of points, right? One for each student at the U of I. So you're going to have this population scatter plot that we don't know. It will have like, I don't know how many students there are at the U of I, 38,000 or so. So it's going to be this population scatter plot with thousands of points. With thousands of points, one for each student at the U of I. And each student will have it'll look like this. Each student will have an X and a Y associated with them. Their X would be what? The number of drinks per week. And the Y would be their GPA. And then we're going to get some scatter plot that we don't know what it looks like. We don't know if it's negative, positive, or what. Okay, it's just in there. And then what we're doing is we randomly draw a sample n points. So we're randomly drawing n of these points, okay? And from those endpoints, we get these sample statistics. An average for both variables, a standard deviation for both variables, and the correlation coefficient. And this is the correlation coefficient. Pretend we got a negative correlation of negative 0.2. Okay? Basically, what we're trying to figure out here is, do we have enough evidence from that negative correlation to conclude there's a negative correlation among all UI students? It's negative in this small sample, but negative 0.2, is that big or small enough? So we're basically just going to look at that. It's similar to doing a hypothesis test, but it's just doing confidence intervals here. All right, so we're going to first we have to calculate the sample slope, okay? So the sample slope for predicting GPA from drinks is going to be, that's B1, right? And what is that going to be? Remember what it's going to be? I'll just write it down. R times the standard deviation of Y over the standard deviation of X. And you don't have to worry whether how these were arrived at. Whether you divide it by n or n minus 1, they're going to cancel out anyway. Okay, so what do we get? We get negative 0.2 times what? The ratio there. And which one's Y and which one's X? Y is always what we're predicting GPA, so GPA is Y, and that's X. Whatever you're predicting is the Y. All right, so we're going to have 0.5 over 5, and that is equal to negative 0.02 points, GPA points per drink. So on the average, it would lower people's GPA by 0.02 points for each extra drink they consume per week. All right, that's the regression equation. But that slope's going to vary, right? So we're going to say how much it varies by. Calculate the standard error and use it to build a 95% confidence interval for the true population slope that we don't know. So remember what this is, the standard error of the slope. And that is what? It's the standard deviation of the errors, which is the square root of 1 minus r squared, times the standard deviation of y, over the square root of n, and then we have to make it y over x, so it looks like that. All right, so we can do this, and we get the square root of 1 minus r squared would be what? 0.04, right? R is equal to that, so r squared is 0.04. So it's 1 minus 0.04 over the square root of, now don't use 2,000, always use your sample size, not the population size. That will never enter into these formulas. So that's divided by 25 over 0.5 over 5. And you can see that's points per drinks. And I got 0.0196. We can approximate it. We'll approximate it with 0.02. Let's do that. It's just easier to work with. Okay, so that is, even though there's so many 0.2s here, it's confusing, but do you mind? Can we just approximate it with that? It's just coincidence there's all these 0.2s. It's just because I made this 0.5 over 5. Okay, now, let's see. Build a 95% confidence interval. We haven't done that. So let's do that. The 95% confidence interval for that slope is going to be negative 0.02. That right there. That. Plus or minus. Theoretically, we should do 1.96 times that. But I just want to do it in my head, so I'm just going to say 2 plus or minus 2 times our standard error. So we get negative 0.02 minus 0.4, so we'll get negative 0.06 to 0.02. Now, since the interval includes 0, this interval includes 0. Yeah, it's more likely. That interval, we can't be sure. We can't be confident, 95% confident, that there's a negative correlation in the population. In other words, the small negative slope could easily be due to sampling error. So we don't have enough evidence. We'd have to get a bigger sample. Do it again. Does that make sense to people? Because that interval, our confidence interval, includes 0, so there might not be any correlation. It even includes positive. So now we're going to look at the t-distribution and look at what we need to do when we have a smaller sample size. So let's take a deep breath and do that. Any questions so far? So this is just going to be a refinement of what we've done so far, refining what we've done for small samples. The reasoning is the same. All right, so I just spilled stuff all over my, oh well, I'm such a slob. All right, suppose we have a small sample. Let's say n is less than 30. And again, we have an unknown population standard deviation, sigma. We should really be using a slightly different standard error and the t-distribution. So let's read the next page and then do this part B, D, do the rest of this using a small sample. All right, so here is what we're going to do. All right, so redefining the distribution for small n. All right. Okay, so there's two things we're going to do. The first is we're going to adjust the standard error. We could have done that with z. Just as our estimate of the standard error of this sample averaged involved dividing by the square root of n minus 1, not square root of n. Remember when we did this back in Stat 100 when we had a small sample and we had an unknown, we're taking from an unknown population where we don't know the standard deviation. We used n minus 1 in our denominator in computing the standard error. Okay, because with 1 point, you have no way to estimate the standard error of the mean, right? You need at least 2 points to do that. So, so the estimate of our standard error of the slope is going to look like this. It's going to be exactly the same, but instead of dividing by square root of n, we're going to subtract 2 off, not 1. And we say there's n minus 2 degrees of freedom. And you can think of it this way, because you can't compute a slope at all with 1 point. You can't get a line, right? With 2 points, you'd always get a single slope. If you just have 2 points determine a line. So you need at least a sample of 3 to sensibly estimate a range of estimates for the slope. So you can see how much it could vary. You can't just do that with 2 points, because any 2 points you'd get a line. You wouldn't be able to see the range at all. So to get an idea of how well the points fit a line, you need at least 3 points. So it's like the first 2 don't tell you anything yet. You need 3. So we subtract off 2. Same with, all right. Now, so this is our formula right here. Okay. And now you could use this standard error. The standard error, you could use it for the normal distribution. It's always slightly more accurate. It's what's called an unbiased estimator. It's always better, but you don't really need it when you're using the normal approximation, because when your n is small enough for that to make a real difference, you know, it makes a much bigger difference when n is small. If n is, you know, the difference between n minus 2 and n when n is huge, when n is big doesn't make much of a difference. So when n is small enough for that to matter, well then the normal distribution is already starting to be inappropriate. So generally speaking, you use the t-distribution and the standard error plus. And when you use the normal distribution, even though you could use a standard error plus, and theoretically it's better to do that, people don't. They just use the regular standard error with n in it, because it makes hardly any difference. All right. So the big difference here is these t-distributions, and the t-distribution is relies on assumption number 4. If the sample size is too small for the central limit to kick in, then here's where assumption number 4 comes in. If the errors are normally distributed, we can use the t-distribution. Remember with the central limit theorem, we don't have to have a normal distribution of the errors because we have a big enough sample size, the central limit theorem will happen. So that's why this normal distribution comes in when you have a small sample size. And it's exactly like what we did when we estimated means. So a good way to remember this is you should use t when the sample size is small, when the errors around the regression line are normally distributed, when you have an unknown sigma, which is otherwise you don't need to use either. You could just, you know sigma, you don't have to estimate it. So this is unknown sigma, then use t. And I use that snut because it just, I don't know, it sounds like a dirty word, and in some ways I think that introducing t so early, like in Stat 100, or the way, not in Stat 100, but the way it sort of destroys your intuition. So I have a negative feeling towards many intro stats classes, not Stat 100, because they introduce it really quickly and you lose your intuition, so I wanted to call it something dirty sounding. That's how I remember it. Like smut, slut, you know, snut, snot. It sounds bad to me. So even though the T is adorable and I liked it a lot before I started teaching intro stats, now I pretty much hate it because it's just a terrible way to teach from the start. Okay? I mean, in the beginning. You guys are in Stat 2, so it's fine, 200, but Stat 1, it's a bad way to teach. So there are two differences between the simple normal z we showed and the t. We used the standard error, and we didn't bother, plus, and we didn't bother to do that for z, we could have, and we used t-curves. Okay, so check out these t-curves. Okay, so the normal curve is the one that's tallest in the middle and skinniest out here. And then you have this family of t-curves. There's not just one. And as the t-curves, they're related to the sample size. So the k is the number of degrees of freedom. So if you have a sample size of 3, then k would be 1 degree of freedom, and you would have the most extreme difference. See how much fatter in the tails it is. So when you have a really small sample, like this would be a sample of 3, this is the actual t-distribution, it still looks a lot like the normal, but has much fatter tails. All right, so what do we want to know? So that means the critical, okay, because it has fatter tails, that means we have to go further out to get the same middle area. So T critical is always going to be greater than Z critical for a given confidence interval. Right? because more of the middle area is contained. See, it's higher with the normal curve. You have to go further out. It has fatter tails. All right, so now let's do, in the last 5 minutes, let's do this problem. So we're going to calculate the standard error plus first. All right, so what do we do there? The standard error plus for the slope is going to be exactly the same thing as this, except what are we going to have here? Let's just do the same thing. Square root of 1 minus. What's going to change? Is anything good? The only thing that's going to change is the n. And instead of 25, what are we going to have? 23. So that's going to make it a little bit bigger, right? And so when I did that, I got 0.0204. It's a little bigger because you're dividing by a smaller n. All right, so now, remember there's a whole family of t-curves, so how many degrees of freedom? The degrees of freedom is equal to n minus 2. 2 points determine a line, so then you need at least 2 points. N minus 2, so we have 25 minus 2, 23 degrees of freedom. And that's where we get our critical value. So we're going to have the same exact thing. The 95% confidence interval is going to equal our sample slope, which is what? Isn't that our slope? That's our sample slope, plus or minus something, and that's going to be the critical value for the number corresponding to 95%. So there's two things you have to look, times our standard error. And in this case, our standard error plus, which is 0.0204. So that's our standard error plus. And then we can just do that math. We just have to get that t. So let's go to the back of the book. And this will be the same t-curve that will be on your exam. Unfortunately, it doesn't show the middle area. It just shows one tail. All right, so one tail. So this is just for one tail right here. So that would be like what? So we want a 95% confidence interval. So that would be, this would be a 95% confidence interval. This is for, that would be the middle area. That's one tail, so double it, right? This would be what? A 99% confidence interval, 98%, etc. Does everybody understand that? Okay, now degrees of freedom, 23. So you go all the way down to 23. And now, as I said, the t critical is going to be a little bit bigger. It's 2.07. That's what we want right there. Does everybody see that? For 23. All right, so that's what we want. We'll put it right in here, 2.07. And when I did that, did all that out, I got a confidence interval that was a little bit bigger than that, wider, because we have, this is bigger. So it's then the other one. So I got negative 0.062 all the way up to a little bit bigger, 0.022. So it was, how does the above confidence interval compare? It's wider. It's always wider. It's wider. Okay? Using t, because t star is greater than z star. And also the standard error plus and standard error plus is greater than standard error. You have more error, so you have more, a wider confidence interval.